Picture this. You're in the exam hall. The clock is ticking relentlessly. You flip open your Cambridge Mathematics past paper, maybe it's syllabus code 0580 or the rigorous 0606, and boom, you are immediately hit with a wall of complex algebra. Deadline pressure is a very real, very physical thing. Your heart rate spikes. You have to break down the story of the question, and you have to deliver the headline, the final answer before time runs out. Welcome to this explainer where we are going to completely demystify these high-pressure scenarios. We're going to build a step-by-step visual toolkit for absolute algebraic mastery. Now, I want you to imagine two totally different students taking this exact same exam. We'll call them Alex and Sam. When Alex sees a difficult question, he totally overloads. He writes down every raw mathematical fact he can remember, hoping the examiner finds something worth a mark. There's zero analysis. Then you have Sam. Sam is terrified of the timer. Sam rushes, completely misses the crucial command word requirements in the prompt, and loses easy marks because of sloppy structure. We are going to look at their flawed approaches, break down actual review exercise questions, and completely rebuild your exam strategy from the ground up so you don't make their mistakes. To fix the mistakes that Alex and Sam make, we need a crystal clear battle plan. Here is our strategic roadmap for today. Section 1, functions and their inverses. Section 2, conquering quadratic equations, and Section 3, cracking polynomial factors. By giving ourselves this clear three-part structure, we immediately reduce that exam anxiety I was just talking about. We are priming our brains for pure logical learning. We aren't just going to solve isolated problems today, we are building an unbreakable mathematical framework. We're going to teach you how to decode what the exam is actually asking for, so you never waste time writing down useless formulas like Alex, and you never miss the key requirement like Sam. Let's get straight into it. All right, let's kick things off with Section 1, functions and their inverses. What's really fascinating here is how visualizing abstract concepts makes finding an inverse function remarkably straightforward. When Alex approaches functions, he just sees a jumble of letters and numbers. He tries to force the algebra without understanding what the math is actually doing. But functions aren't just random calculations. They have a beautiful, tangible geometry to them. If you can see the shape of the math in your mind, the algebra just becomes a tool to confirm what you already know. So, let's decode the actual definition. An inverse isn't merely an algebraic manipulation. It is a perfect geometrical mirror image. Think of it this way. An inverse function completely reverses the action of the original. If a function f maps an input x to an output y, then the inverse reaches out, grabs that y, and maps it right back to x. And when you graph this, the inverse is always a reflection across that perfect diagonal line where y equals x. Now, here's where we introduce our secret weapon, adapted specifically for Cambridge Mathematics, the Peel framework. Point, evidence, explanation, link. Top students structure their math answers just like a solid argument. The point is stating the mathematical rule, like recognizing we need a reflection. Let's see how this framework applies in practice. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, look at this brilliant illustration of why a standard parabola simply does not have an inverse unless we step in and specifically restrict its domain. The first function here, f of x equals 1 plus x squared, is your classic U-shape. If you draw a horizontal line right through it, it hits the curve twice. This means two different x values are giving you the exact same y value. If we tried to build an inverse machine to reverse that, the machine would break down. It wouldn't know which x value to spit back out. But if we slice that parabola right in half by restricting the domain, say choosing x is greater than a specific value k, it passes the test. It becomes a one-to-one function. That is the exact explanation part of our PL framework you need to write down to secure those marks. Let's move to our next slide and watch this step-by-step procedure effortlessly unlock the inverse for a square root function. This is where Sam usually rushes and drops a negative sign. Not us. We use our Peel framework. Step 1. Set y equal to the function, the square root of 12 minus x. Step 2. To break that square root, we square both sides. That's our evidence of algebraic manipulation. Step 3. We isolate x on one side of the equation. Step 4. The final link back to the command word. We do the magic swap. Change the x to y, the y to x, and formally state your final answer as f inverse of x. By treating this as a rigid, non-negotiable checklist, your mark potential goes from 0 to 100%. You literally eliminate the chance of making a structural error. Moving right into our second masterclass, conquering quadratic equations. This is where the magic really happens. Quadratics are the absolute backbone of syllabuses like 0606, 4037, and 4040. We are going to look at the hidden architecture inside these quadratic formulas. We're going to transform those red pen marks on your practice papers into green check marks. It's all about reading the story of the equation and knowing exactly which tool to pull from your kit. Imagine you are under that ticking clock and you see this question. Find the absolute least value of the quadratic equation 2x squared plus 5x minus 3 without graphing it. Alex would look at this and start plugging in random numbers, hoping to stumble upon the lowest one. Sam would try to quickly sketch a messy graph and guess the coordinates. Both of those methods are completely flawed and will cost you precious time. There is a precise mechanical algebraic method to find the exact bottom of that curve. We need an algebraic scalpel to cut straight through the noise and deliver the headline the examiner wants. Enter the mathematics success blueprint. We force the equation into a specific format, and the coordinates for the least value practically jump right off the page. We call this completing the square. And here is how you rewrite your destiny on this question. First, factor out that annoying coefficient of 2 from the x terms. Just get it out of the way. Second, take your new x coefficient, cut it exactly in half and square it. You add and subtract that value to keep the whole universe balanced. Finally, you collapse all of that into the elegant form of p times the quantity x minus q squared plus r. Look at that structure. Because any real number squared is either 0 or positive, the absolute lowest value this expression can ever reach is simply that number r on the end. And it happens exactly when x equals q. It's literally a cheat code to the graph. Now, memorize this matrix. This is your ultimate cheat sheet for those tricky intersection questions, proving that understanding the discriminant is the absolute key to conquering quadratics. The discriminant, that famous b squared minus 4ac chunk hiding inside the quadratic formula, tells you the entire story of the graph without you having to draw a single line. If a line is a tangent to a curve, it kisses it at exactly 1 point. One intersection means one solution, so you set the discriminant strictly equal to 0. If a curve has no real roots, or if the question says a curve lies entirely above the x-axis, it never, ever touches that 0 line. Therefore, the discriminant must be strictly less than 0. Internalize this logic and you will tear through these questions. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, welcome back. Let's jump into section 3, cracking polynomial factors. This is our interactive workshop segment. For our final section, we are tackling massive polynomial equations that look like a terrifying wall of algebra. But don't panic. We are going to use specific mathematical theorems to break them down. Get ready for Challenge 1, the data scan. You have exactly 60 seconds in an exam to look at this complex data source and extract the core trend. How do we unlock the unknown constants a and b hidden inside this cubic polynomial? We have to act like mathematical detectives. The problem will always give you 2 specific clues, usually what happens when we divide the polynomial by certain factors. The secret is that you don't actually do long division. That's what Sam would try, and it takes way too long. We just need to translate the clues from English directly into algebraic equations using our PEL framework. Let's move to Challenge 2, find the flaw. Often students write paragraphs of messy algebra here and lose the thread. Structuring our given data like this matrix clearly shows how to set up simultaneous equations without the flaws. Let's say the prompt tells us x minus 1 is a factor. According to the factor theorem, plugging in a positive 1 for x must leave a 0 remainder, so f of 1 equals 0. That's your first equation. Now the remainder theorem works the exact same way. If the question states dividing by x plus 4 leaves a remainder of negative 50, then plugging in a negative 4 for x must equal negative 50. So f of negative 4 equals negative 50. 2 simple substitutions generate 2 clean linear equations. Solve them simultaneously and you found A and B. All right, Challenge 3, speed writing. You have 30 seconds to write 1 perfect Peel paragraph. Let's walk sequentially through the process, revealing that what looked chaotic is actually a perfectly logical sequence. The examiner tells us x plus 2 is a factor. Step 1, point and evidence. Following the factor theorem, we plug in x equals negative 2 into the entire equation and set it all equal to 0. Step 2, explanation. Since a is the only unknown left, we use basic algebra to isolate it, mathematically proving that a equals negative 2. Step 3, the link. Now that our polynomial is complete, we need to find the remainder when dividing by x minus 1. We simply plug a positive 1 into our newly completed equation and boom, whatever number pops out is our remainder, b. Precise, logical, and guaranteed full marks. We are entering Act 5, the final system. After factorizing the polynomial into a linear and quadratic product, we dramatically reveal that the entire complex equation yields only one single real root. This is how you guarantee top marks. You need to follow 3 rules. Rule 1, command word decoding. The exam asks you to show that the equation has only one real root. Rule 2, Peel framework application. Once you factor out the linear piece, you are left with a quadratic. You get one root from the linear piece, but then you test the quadratic part using the discriminant we mastered earlier, b squared minus 4ac. You calculate it and it's a negative number. Rule 3, time management matrix. Because you knew to use the discriminant instead of trying to solve it, you saved 5 minutes. A negative discriminant means the quadratic part produces 0 real roots. 1 plus 0 is 1. The math perfectly proves itself. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. And before you go, I want to leave you with a provocative thought to ponder. You've seen how the factor theorem logically unlocks real roots today. But think about it. If a negative discriminant means no real roots, what kind of roots is it actually hiding in the complex plane? Would these exact same rules change if we introduced imaginary numbers? Mastering the foundations we covered today, the structure of functions, the geometry of quadratics, and the logic of polynomials, is just your first step into a much wider, fascinating world of advanced mathematics. Keep practicing, trust the system, and I'll see you in the next explainer.